6. Why logistic function? As we already know, logistic regression uses a logistic function. But why is it meaningful for logistic regression to use a logistic function? Logistic regression uses the logistic function, which produces an S-shaped curve to model the probability of a binary outcome. This choice is both meaningful and necessary for these reasons. Let's see these reasons one by one. First, the sigmoid curve of the logistic function ensures that the output is always between 0 and 1. The output is predicted probability, so making it between 0 and 1 aligns with the fundamental properties of probability. The S-shape of a sigmoid curve provides a smooth and continuous transition from one class probability to the other. As the input increases or decreases, the predicted probability changes gradually and predictably. The second reason is its Logos representation. Logistic regression aims to link a linear combination of features to a probability. A linear combination can have any value from negative to positive infinity. The logistic function converts the linear combination into a valid probability. The input to the logistic function represents the logos. This is a natural way to express the ratio of probabilities of the two outcomes in a binary classification. The third reason is that logistic function can handle nonlinearity. Many real-world relationships between the features and the probability of an outcome are nonlinear. The logistic function can represent a nonlinear relationship because the denominator includes an exponential function that varies nonlinearly with changes in inputs. Therefore, even though the underlying model is linear in terms of the logos, the logistic function allows for capturing nonlinear relationships. The logistic function is suitable for modeling binary outcome based on the probability of occurrence of events. The output of the logistic function is always between 0 and 1. This is a suitable range for representing probability because it means the output always falls between 0% and 100% for any input value. The output of the logistic function is a continuous variable and varies smoothly with input values. Thus, the logistic function can clearly express how small changes in input values affect the probability. This helps us understand how subtle differences in the predictor variables affect the outcome. In logistic regression, the gradient descent method is used to find the optimal parameters. The gradient descent method uses differentiation to minimize the error. Since the logistic function is a differentiable function, it is possible to find its minimum value by the gradient descent method. Also, since the logistic function is a continuous function, it is differentiable over the entire range of output values. If the output values are discrete variables, the derivative cannot be defined due to discontinuous changes in the output values. The logistic function's property of being differentiable over all input values makes it suitable for parameter optimization by gradient descent. Finally, but not least, logistic function has high interpretability because of clear decision boundary, coefficients, and odds ratios. As to decision boundary, the midpoint of the sigmoid curve provides a natural decision boundary. If the model's output is greater than 0.5, the instance is classified into one class, otherwise into other class. As for the second point, the coefficients in the logistic regression model are interpretable because the change in logos for a unit change in the predictor, which can be transformed into odds ratio for easier interpretation. Let me elaborate on the relationship between coefficients and odds ratios. First, let's discuss odds ratio. The odds ratio is a statistic that indicates the ratio of the odds of an event occurring between two groups. The odds ratio can be expressed by this formula for the odds of group A and group B, respectively. Let's look at this in concrete values. Suppose the odds of an event occurring in group A are 0.3 and the odds of an event occurring in group B are 0.2. In this case, the odds ratio of group A to group B can be expressed by this equation. The odds ratio is 1.71. This means that Group A has a 71% higher relative chance of an event occurring than Group B. Dividing the probability of occurrence between each other, 0.3 divided by 0.2 yields 1.5, which is a comparison of the ratio of cases that occur to all cases between the groups. The odds ratio, on the other hand, compares the ratio of cases that occur to cases that do not occur. Due to differences in odds between the groups being compared, odds ratios may be more sensitive than comparison between occurrence probabilities. For example, if the probability of occurrence in group A is 0.5 and the probability of occurrence in group B is 0.2, the ratio of the probability of A divided by the probability of B is 2.5. But the odds ratio of A to B is 4. The increase in odds ratio is larger, suggesting the sensitivity of odds ratio. In the logistic function, the odds are modeled by the e to the power of z. Thus, if there is only one predictor variable x, the odds are expressed as the e to the power of beta x. Suppose the predictor variable x changes slightly. If we denote this change in x as delta x, the odds after x changes are the e to the power of beta parenthesis x plus delta x. The odds ratio can be calculated in this way. So it is e to the power of beta delta x. If the predictor variable x changes by 1 unit, delta x equals 1. So the odds ratio is expressed as the e to the power of beta. Thus, by calculating the e to the power of beta for the coefficient beta of the logistic regression model, we can obtain the odds ratio for a case where the predictor x changes by 1 unit. This means that a 1 unit increase in the predictor x multiplies the odds of an event occurring by the e to the power of beta. This mathematical property quantifies the impact of the model's predictor variables on the odds of an event occurring and contributes to the high interpretability of the results. Let's summarize the points. The use of the logistic function in logistic regression is essential for transforming linear combinations of predictors into probabilities. It addresses the need for a model that outputs probabilities bounded between 0 and 1, captures non-linear relationship, and is interpretable and mathematically tractable for optimization. The edge-shift sigmoid curve embodies these characteristics, making it a powerful tool in logistic regression for binary classification problems.